So let's talk about exploring. If you were all alone on your spaceship with no one to talk to and nothing to do, you might go looking around for some friendly crewmates in a place where you could have some fun in the sun. Unfortunately, for words like some and all, there's no guidance system to help them find meaning in the universe. When it comes to the vast expanse of natural language, basic logic just won't cut it. So what's a poor quantifier to do? I'm O.T. Lieberman, and this is the Ling Space.
Welcome to the Ling Space.
When you want to explain the way the universe works, coming up with mathematical models can be really useful, and this applies to language too. The most basic bits of a system like predicate logic can capture the meanings of adjectives and verbs, and it does a good job with connectives like and or. On top of that, predicate logic uses quantifiers, symbols that can represent the meanings of words like all and some. But we have a bunch of quantifiers, not just those two. How about words like few and many and most? Can we use logic to represent these too? Well, like a bathroom break on a backwards planet, that's easier said than done. In fact, in the 1980s, a couple of linguists mathematically proved that no matter how hard you tried, you'd never make it work. Even for a really simple sentence like, most toasters just make toast, no combination of quantifiers and connectives could ever come close to mathematically meaning what we want these expressions to mean. Well, what about if you invent a new quantifier, say one that means more than half? Even with that, no matter what curry of symbols we try to cook up, none manage to exactly match speakers' intuitions about what most toasters just make toast really means. The problem is that we have no way of limiting where quantifiers have to look to calculate whether something is true or false. That upside-down A and backwards E in logic work by scanning through the whole universe and checking every single thing in it to see whether they found what they're looking for. That's how they're defined, and that's how our made-up quantifier M works too. Say there's just one talking toaster in the whole universe, while the rest stay silent and just make toast. Our intuition is that most toasters just make toast feels true. But since most things in the universe aren't toasters, the logical version of this sentence comes out false. It counts everything that's not a toast-devoted toaster against the sentence, whether it's an appliance or not. And since that doesn't match our own intuitions about what the sentence means, that's not the best result. It's also not just this particular logical setup using and. Any other construction, like with or the conditional, will fail in the same kind of way. So we want a way to restrict the space a quantifier needs to look through. Thankfully, we have set theory to rescue us, which we talked about a while back. Instead of thinking of the quantifiers in logic as bounty hunters scouring the whole universe to get the job done, we can think of them as hardworking technicians relating and comparing sets. For instance, in the sentence, all of the crew escaped the squid, we can ditch our logical version and replace it with something simpler. We can just think of the set of all crew members as being a subset of all the people who escaped the squid. So it turns out the meaning of the word all is just like the subset relation. And in the same way, in the sentence, some members of the crew are holograms, the meaning of some can be expressed using the operation of set intersection. The meaning of some just says that the intersection of the two sets it's comparing isn't empty, so there's at least one thing that's both a member of the crew and a hologram. And we can use these tools to talk about other quantifiers too, like no. In no cat wants to be poorly dressed, we can represent the meaning of this sentence by saying that the intersection of these two sets is empty. Obviously, there's nothing that's both a cat and that also wants to be poorly dressed. Most importantly, we can finally get a grip on the meaning of most. For a sentence like most crew members are afraid of Mr. Flibble, we can write out its meaning by saying that the number of crew members who are afraid of Mr. Flibble makes up more than half of all crew members. By mixing a little bit of set theory into the recipe, we've now redefined quantifiers to be fundamentally binary. They take two sets and then, depending on how they're related to each other, spit out either true or false. We've taken our original logical quantifiers and generalized the underlying idea to make it easier to talk about real human language. We made a generalized quantifier theory. But the coolest thing to come out of this is that once we look at word meanings in this way, we find patterns that seem to be universal across all human languages. For one thing, all quantifiers seem to have the property of conservativity, which isn't a politics thing. It's a mathematical property we can spell out using set theory, like this. That means quantifiers only care about the elements in the first set they combine with, and so they ignore anything in the second set that's not already in the first. Think back to our sentence, all crew members escaped the squid. We know that all is conservative because that sentence doesn't care what else may have escaped the squid. And the meaning doesn't change when we reword the sentence as, all crew members are crew members that escaped the squid. It passes our test with flying colors, and we can do the same with some, no, most, and the rest. Now, nothing's stopping us from inventing quantifiers that aren't conservative. Like, we could say that GELF means that the two sets it compares have the same size. So GELF androids have hair means that there are as many androids in the universe as things with hair, and that's a lot. Since our made-up word's all about numbers, though, it has to count through both sets in their entirety. If we try to shrink that second set down to only things with hair that are androids, and there aren't a lot of those, we get GELF androids are hairy androids, which seems to mean something different. In ignoring everything else that has hair, it fails the same test that all the real quantifiers pass. Words like this turn out to be easy enough to imagine, but since they aren't conservative, we don't see anything like them out in the wild. It really looks like this is hardwired into language. Linguists have looked into this by doing learnability experiments on young children between the ages of 4 and 6. Like, take this one. First, the researchers split the kids into two groups and trained them on fake words, like glebe. For one group, the kids got a version of the word that had a conservative definition, but in the other they were exposed to an impossible non-conservative word. Then afterwards, the children were asked to apply glebe in different scenarios to see if they had properly acquired what it means. Turns out the group who'd been exposed to the conservative version managed to learn it, but the unfortunate kids that trained with the impossible version didn't perform any better than chance. So even though we might not be conscious of the math that underlies our sentences, it still manages to constrain what's actually possible, guiding and shaping language in ways that most of us aren't even aware of. So it's definitely worth it to keep exploring. So we've reached the end of the Ling space for this week. If you quantified everything conservatively, you learned that even something as sophisticated as predicate logic can't really do justice to natural language. That set theory gives us an invaluable way to talk about the meanings of quantifiers like all and most. And that when we apply the tools of math, we uncover deep connections that link together all human languages. The Ling space is produced by me, Moti Lieberman, and directed by Denise Prévost. This week's episode was written by Stéphane Herdepies. Our editor is Georges Coulombe, our music is by Shane Turner, and our graphics team is Atelier Muse. We're down in the comments below, or you can bring the discussion back over to our website where we'll have some extra material on this topic. Check us out on Tumblr, Twitter, and Facebook, and try dropping by our new store. And if you want to keep expanding your own personal Ling space, please subscribe. And we'll see you next Wednesday. Shalabimpa!